All right, welcome to this week's 3D GV seminar. Today, it's our great pleasure to have Aniket Bera from University of Maryland giving a talk. So Aniket is right now is a research assistant professor. Is a very productive researcher working across many domains, including affective computing, graphics, right, robotics, and medicine, human computer interaction, and so on. Okay, his research has been awarded 3 times. Okay, at top conferences this year, in this general space of affective computing, AR and VR. Okay, today he will talk about learning affective human motion. Let's welcome.
Hi everyone, and thank you, Shishing, for the introduction. So I hope you all can see my screen, just to check. So yeah, in our everyday lives, we interact with humans all the time, right? So it's becoming more and more important for technologies we develop to model people, their behaviors, interactions, motions, and emotions for different applications, whether be it virtual reality, crowd modeling, games, or especially in this metaverse world, which everybody's talking about, and different applications. So today, I'll be focusing my talk about how to model some of these human behaviors. So let's break it down, shall we? So affective means relating to emotions. So our work is centered around automated emotion understanding methods, which is steadily gaining a lot of traction in current AI research. And by human motion, I refer to body movements such as gestures, gaits. So I work on emotion understanding from such gestures and gaits, which is relatively unexplored in the current literature, especially in terms of social psychology. But they make up a very crucial component of emotion understanding, as we'll see in this 40-50 minute talk. So let's set the agenda for this talk. So I will first talk about the scientific representation of emotions or affects, how humans perceive emotions via different modalities, and the importance of designing automated systems with emotion awareness. Then I'll move to the crux of our research on emotion learning from body expressions, as I mentioned, such as gaits and gestures, which we broadly classify into two different broad, classes, so to speak. So emotion recognition and emotion synthesis. So we've done a large body of work on emotion classification, recognition, but in the interest of time, I'll only talk about emotion synthesis in this talk. I'm more than happy to answer questions related to the recognition and more details later on. So for emotion synthesis, we consider both asynchronous synthesis, which means synthesis from a single modality such as gaits, as well as synchronizing the synthesis of more than one modality, such as gestures and speech. I will elaborate later on some approaches to solve these problems. In the end, I will also touch base on some potential future directions of this entire world of affective computing before I wrap up my talk. So starting with the background, right? So affect is the scientific term for emotions. It's commonly represented as either discrete categories or continuous dimensions. Discrete categories consist of emotion terms that we are familiar with in our daily conversations, such as happy, sad, angry, surprised, bored, and so on. While these terms may be easy to understand intuitively, they're hard to define rigorously. On the other hand, a continuous dimension tackles these problems by describing emotions using three fundamental properties of VAD, valence, arousal, and dominance, and representing emotions as points along these three principal dimensions. So valence indicates how pleasant or unpleasant an emotion is. Arousal indicates how much the emotion is tied to, high or low physiological intensity. And dominance indicates how much the emotion imposes on the observer. For example, discrete emotion terms such as happy may be high valence, medium arousal, and medium dominance, whereas angry could refer to a low arousal, low valence, high arousal, and high dominance. On the other hand, sadness, sad, uh, is somewhere around like a lower valence, lower arousal, and lower dominance. So some recent studies have also suggested that specific these VAD values can be assigned to the discrete emotion terms, sort of making it convenient to traverse between these two representations as and when required. So emotions are perceived from multiple cues and modalities, right? So the most well-studied modality in affective computing are from faces, speech, and written text. By contrast, in our work, we focus on emotion perception from body expressions, such as gaits and gestures, which have been relatively unexplored in the affective computing literature. So there are two key advantages of leveraging body expressions compared to the other modalities which we just saw in the for emotion perception, right? So first, body expressions are fairly easy to observe with low resolution cameras or people like even virtual characters from a long distance, right? Even when the other modalities like faces or speech cannot be viewed or captured. And second, and more importantly, there's many studies in psychology and affective computing that show that humans have less conscious control over their body expression, so to speak. So when I mean less conscious control is that humans can fake these body expressions much less than other forms of expressions like speech and facial expressions. So emotions perceived via these body expressions are much more consistent across different observers from different cultures. Okay, so emotions and body expressions are both very useful in a variety of modern software, including automated recognition systems or digital environments in augmented and virtual reality.
Hi, I'm Morgan, one of the community guides in Facebook Horizon. Here, you can connect with other people as you explore and build worlds together.
So it has applications such as behavior prediction in online teaching, counseling, making virtual agents exhibit human-like social behaviors in real-world situations, and creating like virtual worlds or metaverses such as Facebook Horizon.
Hi, I'm Ellie. Thanks for coming in today. I was created to talk to people in a safe and secure environment.
The same principles can also be extended to social robotics, to teach robots social skills and make them aware of social and emotional cues of humans.
Hey, now, good to see you. How are you today?
I have been busy working a lot. Too much, maybe. How about you?
Not bad.
So also in the other areas such as surveillance for anomaly detection or even medical therapy for like rehabilitation by tracking the changes in body expression patterns.
The C-mill. Together with its highly sensible force plate, C-mill utilizes real-time interactive technology, providing a unique, motivational, effective and safe therapy to improve balance, steady gait, gait adaptability, and dual tasking, fast and effectively.
Okay, so as I mentioned, there's many different forms of body expressions, but today we'll focus more on gaits and gestures, especially in the context of generation for graphics or AR/VR applications. So let's start with generating emotive gaits. So to introduce the work, let us first look at the mathematical structure of gaits. Right, gaits are essentially temporal sequences of body poses constituting a person's walk. So to work with gaits, we require a mathematical description of these poses, right? This is fairly easily achieved by assuming graph structure for for the poses, such as in this example, right? You can see. So the joints are the nodes of the graph, and the bones connecting the joints are the edges. So given this graph structure, we can represent poses by their adjacency matrices, which makes them suitable for mathematical calculations and manipulations. Studies in affective computing indicate that humans observe physiological and psychological features such as arm swings, stride length, head jerks, upper body postures when attempting to perceive others' emotions. So these features are collectively called affective features. And to classify gaits into different emotions, our goal is to train a model that can leverage such affective features. Since computational models are often scale sensitive, we require these affective features to be scale invariant or independent, so that our model can, with different kinds of affective features, can scale, right? So we use two types of affective features, angles and ratios. So following prior work in affective computing, we use a total of 18 affective features, as I show you in these figures. We use 11 angles, including the angles at the shoulders, the arms, and the legs, and we also use 4 distance ratios, primarily measuring arm swings and stride lengths, right? We also use some area ratios to supplement these angles and distance ratios, to in somewhat compensate or cover for the errors in the calculations. For plausible movements, we also need a network to learn from movement features, interframe movement features. So there are features computed from the agent's root joint and the trajectory, and they determine how fast the agent is moving in and in which directions, right? So these include things like, as you see, the root height from the ground plane, the orientation of the root with respect to the tangent of the trajectory at the root position, the speed, stepping phase, and frequency. So the stepping phase determines the elevation of the feet between the footfalls, and the stepping frequency is its time derivative. Okay, so with that background, let's look at at our full pipeline, right? Given a short history of the virtual agent's gait, the intended future trajectory, the intended emotion, and the affective and movement features computed from our gait, our goal is to synthesize the gaits of the virtual agents on that specific trajectory while still expressing whatever emotion we want, right? So we consider the emotion labels to be continuous variables, right, from 0 to 1. So let's say we have happy, angry, sad, and neutral. All of these range from 0 to 1. So 0 indicating that the emotion is completely absent, and 1 indicating that the emotion is at its most intense, is as per the data set we found. So we formulate this as an auto-regression problem. So while we are predicting the future sequence of poses from past sequence of poses, we solve this using an encoder for the past data and a predictor for the future data. So our encoder learns separate latent representations from the joint and other joints. This from the root joint and other joints. So this is because only the root joint is relevant for the trajectory, whereas all the other joints are relevant for expressing different emotions, right? So to predict the future features, we combine the affective features from the emotion labels, the past trajectory, and the root features using fully connected layers in our encoder, and predict using another fully connected set of layers. Given the low dimensionality of the input and output, these fully connected layers were kind of sufficient for our purpose. So to predict the future forward kinematic parameters for the other body joints, we use a temporal network such as the GRU, or the gated recurrent unit, to efficiently learn from the high dimensional data and predict using fully connected layers. So to train this network, we use a combination of a variety of losses, as you can see, to ensure that our gates are smooth, plausible, and emotionally expressive. So we use the motion loss as the difference between the predicted and the ground truth forward kinematic parameters. The pose loss for the absolute joint rotations, the affective loss for the affective features computed from the predicted poses, and the movement feature loss for the route and the trajectory features computed from the earlier predicted poses. And last but not least, we use foot contact loss to eliminate foot sliding in our predicted gates. So once the network is fully trained, we can generate the predicted gates for at least 60 time steps given a history of 10 to 15 time steps, or at least like 4 to 5 times of the history length we have. So let's look at some qualitative results. So here we see emotionally expressive gates for our virtual agents moving on interactive user-driven trajectories. So we see the outputs of the 4 basic emotions: happy, angry, sad, and neutral. So we also see the results of performing transitions between different emotions, right? So since we consider a linear combination of these discrete emotions as our input, we can generate smooth and plausible transitions from the expressions from one emotion to the next as the agent keeps walking. All right, so we conducted 2 user studies with our synthesized gates. For the first user study, we tested the null hypothesis that the intended emotion and the perceived emotion for each of the synthesized gate samples of the same distribution space. So, as you can see from an expert of our results here, that with a 95% confidence interval, we cannot reject the null hypothesis in about 90% of the synthesized gates. So we also look at the intended and the perceived emotions, and in this graph. So, and you can observe that the samples closely match in most cases. So for our second user study, our objective was to validate our choice of these affective features, right? We know in the past slides, you saw that we have like 18 different affective features. So we also wanted to validate if our choice of those specific affective features were useful or not. So for this, we obtained the values of the pose affective features observed by the participants from the synthesized gates on a 5-point Likert scale. So in this figure, the rows represent different emotions and the columns represent the broad, pose affective features. The horizontal axis for each column denotes the Likert scale choices for the corresponding features, with the labels showing like contracted or expanded for the torso, and arms, and slow and fast for the gait pace, and erratic to smooth for gait flow. So, as I've highlighted in the results, we can see that the participants' votes for these broad pose affective features have distinct modes for the different emotions, indicating that the pose affective features vary between different emotions and are consistent across different observers for a specific emotion. Okay, to summarize this work, we have an autoregression method that can generate emotive gates moving along user-driven trajectories. So our emotion model is based on a linear combination of 4 widely categorical emotions, as you saw, happy, angry, sad, and neutral, and can switch between different gates, with different emotions. At the same time, our method, our method has a lot of limitations as well. So first, our formulation considers linear space of these 4 emotions. Of course, as I mentioned before, that we can extend these 4 emotions to more emotions, or even capture a continuous dimensions like the VAD dimension. That's kind of like part of our future work. At the same time, we also use affective and movement features to generate emotive gates. It'll also be very useful to incorporate information relating to the other modalities when we are walking, right? Or even the context of, where you are, what you were doing into our generation model itself. All right, so now we turn onto, I would say, a harder problem of synchronous generation. So here we explore the problem of generating emotionally expressive co-speech gestures. All right, so what are co-speech gestures, right? These are bodily expressions associated with a person's speech, which helps us underline the subject of the matter and the context of the speech. So broadly speaking, there are 4 different kinds of co-speech gestures. So the beat and the dialectic gestures are used for regular rhythmic movements, pointing to people and objects, as we can see in this short video example.
Today, I'm going to talk about race, and I'll start off by sharing with you my story of growing up Asian American.
Iconic gestures, excuse me, are used to express physical concepts or actions. Let's see this video.
Make your bed, they brush your hair, they do small artwork, they do handshakes.
And metaphoric gestures describe abstract concepts, including, affects, emotions.
I was very sorry to tell me that I had breast cancer. I was very sorry to tell me that I had breast cancer.
Okay, so prior works in this area have more or less focused on synthesizing high quality gestures with individual speaker styles. However, they focus primarily on the first 3, the beat, dialectic, and the iconic gestures associated with the speech. In the work we are focusing on, because again, all our work is on behavior and affect, we focus on the quality of the metaphoric gestures for different affects or emotions in this co-speech gesture synthesis, while maintaining the quality of the other gestures. So affective co-speech gestures are not only infrequent, but they also significantly vary based on the context of the speech and or even the speaker's individual styles. At the same time, affective gestures are a crucial component in human-human interactions, as the listener's experience and reactions are often shaped by the perception of these speakers' affects. So now, if you recall, when I was talking earlier about the VAD space of emotion, studies in affective computing show that gestures are good indicators of arousal and dominance. Different valence levels are generally not associated with consistent difference in gestures, and can be inferred with other cues that we saw in the Gates work earlier. So emotions tend to be high arousal, can be high arousal, such as, let's say, amusement, expressed by rapid arm movements, arm swings, or head movements. In contrast, emotions with lower arousal, such as sadness, tend to be expressed with subtle or slow movements. Again, emotions with high dominance, such as pride, are often expressed with expanded upper body, spread arms, upright head positions. On the other hand, emotions with low dominance, such as, say, fear, tend to be expressed by contracted upper body with arms close to the body and collapsed head positions. So as we saw previously with the gait-based research, we also consider a set of gesture-based features, very similar to what you guys saw before for gaits. In this case, we have 15 gesture-based affective features, including 7 angles, different 5 distance ratios, and 3 area ratios. So in this work, we aim to synthesize the speaker's affective gestures to follow individual speakers' styles of gesticulation. So we do not assume that the availability of intended emotions, either as label or VAD values, but we want to learn the desired emotional expressiveness directly from the speech and gestures. So we do not want to impose an affect. We want to we learn it from the way it's spoken. So let's look at one of the synthesized examples to see what it really means, right?
Out into a wider space beyond. I was, I believe, ecologically bored.
We see that the speaker's arm movements matching his frustration on the word bored. Let me play this video once more so you can see.
Out into a wider space beyond. I was, I believe, ecologically bored.
So to be able to synthesize such affective gestures, our key contribution is to learn an efficient set of latent affective features based on body postures, head positions, and arm movements. This is in contrast to our previous method where we used pre-computed affective features, as they may not efficiently or exhaustively capture all different emotion expressiveness, especially from gestures. So additionally, to sync our affects in the synthesized gestures with the affects in the input speech, we also designed an MFCC encoder. So this encoder maps the speech-based affective cues such as prosody or intonation to learnable latent features and guide the gesture synthesis. All right, to synthesize co-speech gestures, we need to consider both the source speech and the individual styles or speakers. Specifically, we take into account the raw speech audio of a speaker and the corresponding text transcript in a natural language as complementary information to safeguard against the noise in the input data. We also use the speaker's unique ID in the data set and a short sequence of seat poses, and then synthesize the affective gestures while still maintaining the style, right? So we use affective encoders to encode the speech, text, speaker ID, and affective content into the seat poses into latent features. So we use a text-based encoder based on fast text to encode the words into latent features. We also use the speaker encoder to encode the speaker IDs into a latent distribution space. So to encode the speech, we transform the raw waveform into melt frequency Keptrel coefficients, or what I was saying, MFCCs, and their first and second order derivatives. So MFCCs are useful for identifying speech-based affective cues such as prosody or intonation. So we also design a set of convolutional neural net layers to obtain the latent features from these MFCCs. So I want to sort of take a moment here to explain that MFCCs are not really closely dependent on the speaker's words, but rather on the speaker's verbalization of those words. So they are kind of better suited than just the raw speech waveform or the text to extract affect or emotional information from different sentences with similar or different affect. So we also design an affective encoder which takes into account these poses, these initial poses, and then transforms them into latent gesture-based affective features. So to achieve this, we learn from body movements at two different levels of hierarchy. So the first one is at the level of the individual bones, where we encode the relative movements of the bones into a feature representation. To capture the relative movements, we consider a two-hop neighborhood of each bone to define the spatial adjacencies. In other words, we consider the two bones to be spatially adjacent if they are, A, they share a joint, B, they are connected to two ends of a third joint, and C, for temporal adjacency, we consider the same bone at two different adjacent time steps, both in the past and in the future. So with this, we can efficiently encode the differences in their relative movements for different affects. To perform encoding, we utilize spatial temporal graph convolutions, or STGCNs, which are commonly used for computing features from localized dependencies in graph structured data. So the second level is at the level of the three upper body parts, the trunk and the two arms. So these three upper body parts capture in some way the macroscopic body movements, such as raising or crossing arms, bending, straightening the trunk. So at this second level, we assume that both the arms, do not necessarily need to be adjacent to the torso, and they need to be adjacent to the torso, but not to each other. Since the movements of, let's say, one arm does not need to influence the movement of the other arm, right? So, excuse me. To consider the temporal adjacency similar to the first level, we again use STGCN for the feature encoding. At the end, we want to reduce the dimensionality of our latent affective features. We pass them through the outputs of the second STGCN through a set of convolutional layers, capturing the interdependency between these intermediate layers, intermediate features. Okay, coming back to our full encoder, we then proceed to synthesize the gestures from the four latent features by concatenating them through a bidirectional gated recurrent unit, or bi-GRU, which provides a temporally related intermediate features, which we then transform into output pose vectors using a set of fully connected layers. We term this whole thing as our generator. Of course, just using the generator by itself, we can't ensure that the gestures we get look realistic. To achieve that, we need to couple our generator with an adversarial discriminator that can distinguish between the original and the synthesized gestures. So we then pass the synthesized gestures to our discriminator along with the corresponding original gestures of the speaker. We again make use of the affective encoder to transform both the gestures into the per time step latent affective features to discriminate them based on the affect information. Again, we use a bi-GRU and a set of fully connected layers to transform the latent features to a single dimensional variable where we can apply the sigmoid function to obtain the soft binary class labels. We can then efficiently train this discriminator to optimize on these labels using a cross entropy loss. So correspondingly, the goal of our generator is to synthesize gestures that our discriminator cannot distinguish from the original gestures. So once the generator is fully trained, we can then use it to synthesize our desired affective co-speech gestures. Okay, so let's try to look at some qualitative comparisons of our synthesized gestures on the kind of popular benchmark TED gesture dataset. So this dataset consists of videos in English, different speeches at TED Talks. So
out into a wider space beyond, I was, I believe, ecologically bored.
So here we want to compare it with, our method, gestures from our method, with another method which called the GTC, which was quote unquote the state-of-the-art method, before ours. So their method synthesizes gestures based on speech, text, and the speaker identity, but not body expressions, not affect. Now let's see the difference between their method and our method, and I'll talk a little bit more about the difference. And I'll maybe run the video again so you can clearly see the difference.
Out into a wider space beyond, I was, I believe, ecologically bored.
So we can see that the synthesized arm movements, and I showed before, indicate an expression of frustration on the word bored. We also know the synthesized, both the gestures, GTC and ours, they differ from the original speaker, right? So this is both expected and desired. Both the methods tend to aim to produce variability of speaker styles rather than faithfully recreating the exact original gestures. So let me replay this once more so that you can clearly see the difference at an affective word bored.
out into a wider space beyond. I was, I believe, ecologically bored.
All right, let's look at some more results.
As a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit.
So in this example,
as a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit.
So we see a swift arm stretch on the synthesized gestures, kind of expressing the speaker's happiness on the word excited. Let me play it once more.
As a product developer, I started my process of research. I was very excited to find that there was a product out there called the Clean Birth Kit.
So we also experiment with two ablated versions, one without using the affective encoder part of the algorithm, where we replace our MFCC encoder with a convolutional network of the GTC, the older method, that directly takes into account the raw speech waveforms. So let's look at the original video.
The contrast between the scenic environment I knew and this smog-covered skyline stirred up something within me. I was appalled by the possibility of the city of bright and vivid sunsets being overrun by a dull haze.
Now let's look at the three different ablated versions of the algorithm.
The contrast between the scenic environment I knew and this smog-covered skyline stirred up something within me. I was appalled by the possibility of the city of bright and vivid sunsets being overrun by a dull haze.
So, I mean, it's kind of difficult to see it first. I can play it once more when I after I describe it. So without our affective encoder, our network can only generate like beat and dialectic gestures. And without the MFCC encoder, our generator cannot, simply cannot generate these emotional expressiveness. It cannot sync with the speech, such as the word appalled in this example, right? Look at this one last time.
The contrast between the scenic environment I knew and this smog-covered skyline stirred up something within me. I was appalled by the possibility of the city of bright and vivid sunsets being overrun by a dull haze.
Whether in tech or finance, sports or the service industry, every day we seem to hear another story about an abuse of power or another grossly inappropriate workplace behavior. People are furious.
Let's look at some of the examples. So I'll just briefly go, I think because of time, I don't want to describe every video in detail, but you can see the differences.
Whether in tech or finance, sports or the service industry, every day we seem to hear another story about an abuse of power or another grossly inappropriate workplace behavior. People are furious.
Okay, so, result time. we compare compare with the qualitative. We also have some quantitative evaluation metrics with the two common benchmark data sets, right? So MAGE, as you can see, or the mean absolute joint error, measures the difference between the absolute joint positions of the predicted and the original gestures. MAD, or the mean acceleration difference, it's a difference between the original and the predicted joint accelerations. Or the Frehe gesture distance, or the FGD, which measures the difference between the distributions of these latent features between the original and the predicted gestures. So, I mean, you can clearly understand that for our experiment and what we are trying to do, the most relevant metrics would be the MAD and the FGD. So the MAD indicates how closely the original and the predicted joint motions or movements match. It's kind of a good indicator of how expressive our predicted gestures are. On the other hand, FGD has been shown to align well with the perceived plausibility of the synthesized gestures to human observers. So a lower FGD is desirable to gauge the quality of our synthesized gestures. So as you can see from the table, that our method consistently outperforms the current baselines on all the three metrics on both the data sets. So it's very important in this entire field of gestures and gaits and expressions that we conduct real user study, right? Because everything is very perceptual in nature, right? So we conducted user study, 2 different user studies as well, to generate the perceptual quality of our synthesized gestures. So the first part was to determine how plausible the gestures appeared on a 5-point Likert scale. So if you've observed that 15.28% more participants marked our gestures either 4 and 5 compared to the gestures synthesized by the oldest method, GTC. Interestingly, and this is something to maybe even debate upon or discuss later on after this talk, is that 3.82 more participants marked our synthesized gestures, 4 and 5, compared to the original gestures. So they preferred, 3.2% people preferred our gestures more than even the original gestures. It simply indicates that the participants found the synthesized gestures to have a visual quality which is comparable to the original data. So original and R, they have different visually different gestures. So 3.8 is more like noise about some people preferring our gestures over the original or vice versa. So our second part was to determine how well the gestures synchronized with the corresponding speech on a Likert scale. So again, we see that 13.2%, 13.3 more participants marked our synchronization quality either 4 or 5 compared to the earlier method, and 4.6 participants marked the synchronization quality of 4 or 5 compared to that of the original speakers. Again, indicating that the participants perceived our gestures to be well synced and expressive as the original gesture. I like to point out that we haven't yet looked at hands. So even when we're talking about the original, it's just talking about the gestures without finger motion. So clearly there could be some discrepancy of how it would look once we actually add finger expressions into the pipeline as well. Okay, to summarize this work, we have a generative adversarial network to synthesize co-speech gestures with affective expressions. We do not use explicit emotion labels, but learn appropriate expressions from the speech and gestures. So in contrast to our previous methods, we learn affective features automatically from the data instead of sort of predefining them. Also, we design an MFCC encoder that leverages MFCCs computed from the raw speech waveforms to sync the synthesized gestures with the speech-based affective cues like prosody and intonations. Of course, our work also has limitations. Firstly, we do not build a mechanism to control these affective expressions, but compute them automatically from the input modalities. Of course, we plan to investigate the interface between affective expressions, from speech and gestures, especially when contradictory cues like sarcasm or joy, right? Sarcasm or like irony, right? So these are the kind of things we cannot do at the moment where there's contradictory expressions between the different cues. Secondly, we plan to use a finer representation of poses in the future, since affective expressions and gestures are often associated with subtle movements which are we are unable to capture with our present representation. And last but not least, our method uses only upper body gestures with a fixed root. In the future, we'll of course plan to extend this to the whole body, maybe even leg motions. Even though when we are talking to each other, there's more gestures on our upper body, there are more finer level gestures which sort of trickle down to the lower body as well, which we plan to do in our future work. All right, so of course, this is the part which I unfortunately due to time I could not cover, but just to briefly talk about it, like to enable better conversational agents, we also need to build and develop better perception algorithms of these affective states, right? So beyond the traditional realm of graphics or affective computing, we're also working and collaborating with other vision and AI researchers to leverage the machine learning based generative methods I just talked about to be also able to efficiently model modalities like facial expressions, speech, voice modulations, expressions, or even context in real time. So before wrapping up my presentation, I wanted to give sort of a brief glimpse into some of our current and ongoing projects and applications leveraging the emotion perception work and some future research questions. Okay, so my students and I are also working on a funded project with the behavioral health experts and psychiatrists at the Maryland Medical School to develop a technological approach to not only assess patients' behavioral state, but to also create virtual humans that can respond in real time using human gestures and emotional cues, eventually to improve patient care and engagement. So our project is looking at people who are the most at risk of depression, or people who have experienced disparities in healthcare. We are currently in the process of applying for a clinical trial grant, but unfortunately, because of patient confidentiality and privacy issues, I would not be able to show any actual patient videos and audio. All right, so we also designed what we call a next generation AI-driven human-computer interaction platform, Project Dost. So it combines detection and generation work to create realistic interactive avatars designed to have conversations and sort of behave like humans, not only in terms of content, but as you can guess, also in terms of emotional and behavioral expressiveness.
Hello, I'm your artificial intelligence-driven virtual conversational assistant. I can help you with daily chores, tasks, and will be able to make smart conversations.
My gestures, facial expressions, and speech are generated in real time using state-of-the-art research in affective computing, emotional modeling, character and speech generation, and virtual reality.
I was designed at the University of Maryland. I can not only speak different languages but can also generate cultural and emotion-sensitive gestures and expressions.
In the future, I will be able to understand you better, learning from you and your emotional states.
Approach is a transformer-based learning method to interactively generate emotive full-body gestures for virtual agents aligned with natural language inputs.
So it seemed like there was some weird video jumps in the whole thing, maybe because of too many applications on my computer. But I mean, you can go to this website, those.cs.umd.edu, to see the full video and a lot of other related research. So we also took this project into a new direction with virtual therapy application in augmented reality. Of course, it's very much in its initial stages, and I highly recommend folks to check out the website in a few months to catch up with the progress.
Hello, who are you?
I am a conversational AI created by the University of Maryland. You can call me Dust. How was your day?
Stressful.
I want to help you manage that stress, Jason. Let's talk about stress management techniques. Are there any techniques you know?
No, can you tell me some?
Yes, it is important to have a healthy lifestyle that manages your stress. I recommend that you do physical activities that help you release explicit and implicit stress. You should also sleep 7 to 8 hours every day. Sleep is essential, and lack of sleep is a major cause of stress.
Wow, thank you.
My pleasure. Have a good rest of your day.
All right, so clearly there's a lot of exciting research avenues, multiple research problems, sub-problems, which we will pursue over the next few years. So one of the most critical things which we want to explore in the immediate future is facial expressions. So extended further from synchronous generation of speech and gestures, we also plan to build a method to generate both facial expressions and emotionally expressive gestures synced with speech. So I mean, you saw the project, those videos, a few minutes ago. Even in that, the most what we were doing is essentially this part of the mouth, like lip syncing. We weren't really doing full face gesture generation. So there have been some work, promising recent work on synthesizing co-speech facial expressions, but most of them lack, the affective space of facial expressions. So our plan is to build on those approaches for face generation and integrate them with our method for gesture generation that can sync with facial expressions as well as gestures with each other and with speech. So there are many research questions which we need to address, right? One is to determine a set of possible affective features for facial expressions to generate highly plausible micro expressions. So another question is how to sync the facial expression with gestures. We need to understand that, this part of the body, the face part and the gesture part of the body, there may be more, they may not be always a one-to-one relationship. So to understand the relationship between different kinds of components in our body, we need to understand their physiological and psychological relationship. Right? As we attempt to synchronize more modalities together, we also need to be very mindful of the resulting uncanny valleys, right? Which actually can grow to be larger than the sum of these individual parts. So, maybe many more user studies to understand and optimize the quality of expressions. There's substantial cultural differences in how people use body language to communicate. Sometimes it's obvious, sometimes it's very subtle. At the end of the day, if we really want virtual agents to talk like us, behave like us, understand our differences, show our differences, we have to learn from a diverse set of cultures, races, countries, and genders. And clearly, there's a long journey ahead. With that, I would like to conclude with some final acknowledgements. None of this research would have been possible without my wonderful, diverse, and extremely set of talented students. Special thanks to all my advisors and industry collaborators. And last but not the least, like to thank my funding agencies for believing in my research and paying the bills. Thank you.
All right, thanks a lot, Aniket, for a very nice talk. A lot of visuals and with both breadth and depth. So let's now move to the panel session. It's our great pleasure to have Angela Chen from Simon Fraser University. Angela works at the intersection of graphics, AI, and natural language processing in particular, and she has done a lot of pioneering work at the space of natural language processing and the 3D models. So let's welcome Angela. Can you hear us?
Thank you so much, Qixing, for inviting me and for the nice introduction. And thank you, Aniket, for the very, very engaging talk. I definitely learned a lot. It's very interesting work.
Maybe let's start with Angela. If you have any questions regarding the talk, maybe feel free to have a discussion here. So you have the, maybe you can start.
Yeah, I guess I did have some questions. I guess so. Yeah. So maybe my first question will be about the second project you presented. About the. So one thing that I'm kind of curious is that you have this very nice, going from spoken text to gestures. And one thing that I was wondering about is that have you considered working on not just like say TED Talks, but more like where you have actors or actresses like in movies doing different scenes, so they're actually doing more exciting stuff.
Yeah, absolutely. I mean, I'll be very honest here. The biggest problem for this whole project was trying to get a data set where we have a clean set of extracted upper body, like the vision part, hoping that somebody, like the vision researchers are solving that part of extracting the poses. I would be more than happy, and we would love to work on, more kinds of actions. So the TED gesture data set and there's another EMDB Trinity data set are the more common ones where we have either motion capture data or like extracted data, but then manually cleaned up, noise cleaned data. So yeah, I mean, Angel, I mean, I would be more than happy, and I would love to go beyond TED, because TED imposes a big restriction on the kind of videos as well, right? I mean, TED is more of a one person speaking to a crowd. It's not a one-on-one conversation, which from movie data sets, as you rightly mentioned, maybe we definitely want to do it.
Okay, so the big bottleneck there, I guess, what you're saying is really just getting the data, but it's not that it's from what you're saying, it's like you can't just work with just say video data, because there's a lot of video data, but you actually need to have the pose extracted.
Yeah. I mean, there's good pose. So we've started to use, as post extraction methods are getting better with every CVPR, every ICCV, conference, we are trying to get in more and more of this. I mean, I remember 5 years ago, even so, for the GATE project, the first project, we earlier were using only motion capture data, but now for most of the gate-based research, the gate extraction is actually pretty good, like in terms of revision methods. The gestures are still not, I think it's still not there yet. Maybe 6 months from now, I'll say that we have solved the problem, we can do any video.
And do you think, just to follow up on this a little bit more, do you think so? So for the gait one, I guess it's kind of a whole body movement. Correct. And so while for the gestures, you're kind of more focused on the upper body.
Right.
And is it that, do you think like maybe so I guess I just talked about movies because the movies are cool, but I guess maybe part of it is maybe having this like data, like some starting videos, let's say, that's maybe somewhere in between the complexity of a movie scene where you have so many people and maybe they're including each other, and maybe but maybe a bit more complex than TED, where maybe you do have two people talking to each other.
Yeah. So you, if I'm understanding the question correctly, is like, can we start off with simple videos where just there are two people interacting with? Yeah, definitely. That we can do right now. I think that's not that, it won't be that difficult. Yeah.
And in that case, do you think the pose extractions, like for the gestures, would be actually usable?
I think so. So what I will say is, in the medical project I was talking about, like the therapy project, we actually gave patients, are actually like the small phone, which we, it's $100 phone. We gave all our patients to put this in front of like their therapy, like this, so these are online teletherapy sessions. We gave them a phone. We had a stand and stuff like that. So that was pretty accurate because the phone was stable. It was only looking at the upper body. We could extract the gestures from that. I would say almost, I'm not going to say close to like motion captured, but 80% there or 90% there.
Mm-hmm. Yeah, but maybe enough for you to start to use it.
Yes. Yeah. So I think what will happen, and this is, that's a very, very good question, because we were discussing with my students as well that if there is something which are like micro expressions, like subtle face movements, we worry that those will get lost. But again, that said, maybe motion captured data sets are also not 100% accurate, right? They also have some smoothness constraints already applied. So, but yes, we'll start with that. We can't do a lot, but good starting point for sure.
But that's great to know. I was just kind of curious, what were the bottlenecks that from your current work to doing movies.
Yeah.
So you mentioned, so maybe I have another question about that, follows up a bit about the mental health therapy. So
yes.
So you said you're starting some clinical trials?
Yeah.
That sounds very exciting, but at the same time, for me, so I have to admit, I do I work with tables and chairs, and they're very safe things in the sense that I don't have to worry too much about privacy concerns mostly, and I don't have to worry about breaking the table versus, if you're actually running the clinical trial, do you worry that, if your technology is not good, would it adversely affect your patient, the patients? Do you worry about that?
Well, 100%. Let me put it this way. I wouldn't have even gone into that medical side if I didn't find a very good collaborator who was very excited about this whole research. And she said, and like my collaborator in the medical field, she said that let's do it. I mean, we might have to go through 100 different IRB approvals or 100 different, maybe even FDA approvals if it actually goes to a certain point. But we'll spend more time on those approvals, but it is, so right now our clinical trials are, so we have a big chain of therapy centers like connected to us. So we pay them like every patient $50, $100 to come and do this session. So we are still learning. So the clinical trials will definitely take more time. It's not going to happen the next 6 months, but at the same time, I think it is necessary to do any amount of validation. I mean, I sometimes I feel like as CS researchers, we love to show, oh, this is so good, we can do this, but then I was talking about this like, oh, my work can do therapy and all these things, but unless I test it on real patients, my claim will be as useless as so it'll take time, and fingers crossed. That's all I'll say. I'm worried for sure, but I think what motivates me are my collaborators in the medical school.
Okay, that's great to know that you have like good collaborators that can help.
I could do it on my own. There is
yeah. Maybe kind of a related question is that also because you are doing these say generating gestures, do you also worry that maybe one day you will have your little avatars on the internet for anybody to use? But so I come from the NLP, and there's some well-known stories of some chatbots that when they deploy them, it would just like say very bad things. So maybe my question, to make it a bit more focused other than are you worried, is that what kind of safety mechanism would you want to see put into place before you unleash your
unleash the worst? Well, I don't want to deflect the question, but I think I'm for this work, the conversation part, I'm more or less, so actually the conversation part I'm relying on NLP collaborators, right? What to say as a generated, what to generate. But as you're saying, the gestures themselves, so what as I briefly mentioned this in the end, that gestures are very culture sensitive, right? If we just do something and send it out to the world, something can be really insensitive to certain part of the country or certain part of the world. So, I mean, we worry about it all the time. Literally, so our hope is that as this research progresses, the research becomes a little bit more inclusive. Like we get data, as your first question that, can we do from movies and all data sets? Our real hope is that the post-estimation methods gets better, and when we can learn from different cultures, different genders, different representations, hopefully, fingers crossed, hopefully this will be slightly better. It won't solve the problem, for there's no way, but at least from our side, we are trying to do make something a little bit more inclusive, because culture differences in gestures we were looking at are insane. I mean, I only have, like, when I came to the US 10 years ago, it took me a while to adjust to certain kinds of gestures, certain kinds of things in the US compared to where I was from in India. So
yeah, but I bet it's something that most people are not even aware of, in the sense we just unconsciously gesture.
Yep.
That's great.
It's a long journey, that's all.
Okay, so do you have more questions, Angela, regarding the talk?
I guess I could ask more, but maybe
maybe
also have
so maybe let me insert one question, then you can have maybe 1 or two or three more questions. Okay, so okay, that's a nice talk. So I'm a geometry modeling background. Okay, I have so basically so I would like to ask one question, right? For this kind of affective computing, right? From the modeling perspective, do you think the current representations of this kind of humans is sufficient? Do you think we should model more like softer details like muscles, like this kind of like fingers, combined with like the more detailed human model? Or you think that right now the state of result is sufficient, right? So it's not really a critical issue from this aspect.
100%. I cannot wait till the day that I can use a full body higher quality mesh represent like a deformable sort of representation for the entire. I think skeleton will still be a part. I mean, it can still sort of guide things, but a full body more like a mesh representation, like a finer quality mesh representation would definitely be very, very important. And that's something I think our next project will have, at least in terms of, you know, because these muscles are like flexible muscles, right? I mean, just gestures cannot capture a lot of things, our neck movements and all. We kind of throw everything to a gate estimation. I think a full body mesh representation will immensely help this affective computing research for 100%.
Okay, thanks. Yeah. Do you have more questions? Like,
I can have a couple more. I
okay.
really from the
more the better.
Okay, the talk I think is very great and very interesting. And I wanted to ask you a bit, Aniket, whether, you know, so for the affective computing, or, you know, when you have these gestures or you have the emotions aspect. So I think we tend to have broadly what am I trying to ask? I'm trying to ask basically, so, you know, we can bucket the human emotions, right? You gave a very nice background on how we can categorize emotions and things like that. And I was wondering, how fine-grained do you think we need to go down the emotion chain, or is it sufficient to have, like, say, 4 emotions? You know, do we need to have more?
Right. So that's actually that's a very good question, because the reason why I think we need to diversify emotions a little. I mean, the more emotions objectively, those are better. But the reason why we stuck to 4 as opposed to, let's say, 20 is twofold, right? So when we started this entire research like 6, 7, 8, 10 years ago, you know, our data sets, even like the gestured data sets, they weren't labeled with emotion. So we had to go and ask people to label it. We used MTurk and other agencies to label these data sets. The problem is, the more number of emotions we give for people to label, the more confusing they might become. So happy, angry, sad, neutral, they're kind of basic, you know, and very simple. And in some way, a combination of these, you know, we know, okay, this is 20% happy, but 30% sad. So we can do many more emotions just looking at these 4 as well.
Okay, so you're...
Yeah, go ahead, sorry, go ahead.
So maybe what you're suggesting is, instead of having, say, like 100 different emotions, but having like maybe some kind of like the little the VAD model, where you have these different dimensions that you can tweak. And I guess that's also the way you had your emotions, where you had the four emotions, but they were not mutually exclusive. So so maybe you're suggesting that, maybe, I don't know, maybe it's 4 enough, maybe we need more, maybe 8, but some of these that can be tweaked.
Right, 4 is not enough by me. It's I think it's easy as a starting point to get people excited about this whole area of affective computing, but we have done some paper where we had like 17 emotions. Like, it's one of the papers I didn't show in this slides, but we had so much confusion between a lot of the emotions. Like, many emotions were like happy and, let's say, joy. Like joy and happy, people are like, okay, this, like, joy may be more arousal than happy. Like, there's so much confusing. So I think we need to pick maybe 6 or 7 well-distributed emotions in across the space, so we can generate the other emotions based on the weights of where, how these emotions are spread out. That's I think an easier way.
Okay, I think that's a very good answer. That's like I can't agree with it. Yeah, but maybe related to it, but not quite the same. Is that so? Again, I do some work. I don't really know what kind of person am I. Am I natural language? Am I like do some 3D stuff? But anyways, I do think about natural language, and so here is like, so emotions, even the four emotions, we use English words to label them, right?
Right.
And so my question here is more of, do you think that having this well-defined taxonomy of emotions is good, or if you just let it be more freeform, let's say, just have people say whatever they want, would there be some benefit to that?
It's it's something we are thinking of. I mean, we have thought about. I think like with Shishing also, we were discussing one of like, can we give a sentence or a structure, like just a sentence, like describe this thing. Like if you see a video, describe what it is, and then based on the description itself, can we learn, what the affect is? That what you're kind of saying? Is that like rather than asking them to label ABC, let them say whatever they feel like? Is that what?
Potentially, yeah, and maybe what they say is they also say, oh, I think this person is really frustrated. He's kicking at things.
Yeah.
So it could be a mix of that when they describe it. Could it be a mix of of emotion words plus non-emotional words? Yeah.
Yeah. Actually, that would be helpful. There is a Yeah, I think what for many of those, there's this EMDB data set where they have the text of the gestures. Of course, text would not be good enough. That's just one modality. But what you're saying is let people also talk a little bit more about the video, not just the emotion, like some other attributes, like other psychological attributes. Is that correct?
Yeah.
I think that would be helpful. I mean, I need to. That's a good suggestion, actually. Okay, yeah. Let me think on that and get back to you.
Okay, I was just like wondering.
Yeah. No, that's a very good suggestion, because constraining, and this is something we have learned from psychology, our collaborators, that constraining the observer has good and bad aspects. The good aspect is you get to force them to mark certain labels, so we know what we want. But the bad aspect is you're forcing them, so you might lose out something, or he or she really wants to say about the video. And what you're suggesting, like bridge both the worlds in some sense, right?
Yeah, and this is something like, there's always this dichotomy between like, because I guess in NLP, the focus is on the language, right? So of course, there's certain things we will also classify, we're all into classification, but at the same time, there is certain, there's this very long tail of language where, and each word, has subtle different meanings, like your example of happy versus joy. They're very close, but then maybe they're a little bit different. And maybe if you allow maybe to capture something that maybe even when you try to have your four-dimensional or 8-dimensional or however many dimensional they try to do to get people to label, and they don't quite get.
No, that is interesting, because there is a data set, I forget, it's a Canadian data set. I can share the paper with you later. Not not exactly that, but it's a big collection of like 20,000 words or something, and every word is mapped to a VAD value. So I don't know if that's useful really, but it's also interesting that every word has some affect associated with it, or I don't know how they captured it. I think they asked MTurkers. Yeah, I think they spent like $1 million on MTurk and asked people to rate all it. But no, what you're saying is actually very relevant, important, and something I think we should look into, at least for future projects.
I just think it's very interesting.
Thank you.
Yeah, so Qixing, I don't know if you want to
Okay.
continue to ask
So
questions.
let's move to the second one. Second round, like more open questions. Okay. So in fact, that I prefer two questions for discussion. So in fact, one is kind of interesting, right? If I think about from outsiders, so Angel, you worked a lot with 3D models, right? So Aniket present the 3D like this the virtual humans. So 3D models, right? So if you think about the digital copies of physical objects are designed to be used by people, right? So this meaning that this affordance is something that very important. So I want to hear for you, for example, the intersection between this kind of affordance, right? Meaning the interaction between humans and the 3D models, right? And this kind of speech and NLP, right? How this fits into your research and how this community should look like 5 years from now, etc. Like maybe we start with maybe Angel. Do you want to start, or maybe Aniket? Okay, so I think this is relevant to you, right? So you right. So for example, how to insert like this kind of furniture models, like this physical objects into your research. Do you think like for example like having this kind of a background environment in this kind of virtual environment would be beneficial, like humans interacting with,
like for me or in
for you?
Okay. Oh yeah. So I think that is important, right now.
That is a tough question, I know, but
it's like what we're doing now. It's a very initial stages of what these humans will end up doing. These virtual humans will interact with objects, right? As I'm sitting in a chair, I'm looking at these things, I'm interacting with the objects around me. This interaction, I believe, will also lead to affects. Like I'm walking, I stub my toe on the table, right? I'm suddenly like frustrated or angry or whatever, right? So I think interaction with even non-living objects can lead to a change in emotion or affect, and that I think from a broader point of view, it is very important. And I think modeling this speech or understanding of the scene with human interaction or non-human interaction, that needs to be definitely we don't do it now, but it will happen either today or tomorrow for sure.
Okay, maybe Angel, do you want to share a few words on this?
Yeah, I think so. So I started my question about asking about generating gestures for text that goes with a movie or actor, and in my mind that would be so cool. Anyways, that's still something I think is very interested in. But the people, they don't just talk to each other, they also like interact with objects. And so it would be kind of interesting if we can have a human that can open a microwave, and maybe they can open up microwave angrily. Maybe they jerk it open, and or versus they are kind of depressed and they are just like tired, and it's very challenging. I don't know. I think that'd be really cool, and it makes this idea. I guess I'm trying to really because Aniket had such a nice talk, and I'm just thinking about all emotions now. But it will make just this interaction of a human interacting with an object so much more richer. Most of the time, I just think, okay, if we can only get a hand to the microwave door and pull, that will be pretty good. But
Okay, so the final question is related to potential applications, right? For them, besides medicine, do you think, my general question is, do you think this can be beneficial for education, right, for kids, right? So I want to hear your thoughts on this. Maybe again, we just start with Aniket, then we move to Andrew.
Okay. Yeah, I think, and I don't want to future brag in terms of what our research can do, but I think anywhere there's a real person, there like a teacher at this point, or there is some aspects which we can in fact, there's actually some work on virtual teaching, like virtual teachers, right, like character, and I feel most of them are so robotic. They're, I mean, I don't know if I should say this, boring and many other things, because the avatar or the character looks so rigid. They're like, do this, do this, do that. And it's just more. And I think if we can bring all these ideas of like more not necessarily just from the gestures, but even from the speech community, like how to generate speech or language or content in the more affectual space, right? Like I always say this, like you can say the phrase, I'm like, if somebody asks a question, how you're feeling, you can say I'm okay in 5 different ways. You can say I'm feeling okay, or I say I'm feeling. So all these differences, either from a gesture point of view or a speech point of view or language point of view, will make all these applications, whether a teaching application, I think social robotics, I think we briefly presented a small video of these Pepper, or like these small robots with arms and limbs. Of course, the degrees of freedom are more limited, but even in that limited degrees of freedom, these applications, I think, can get a little bit more human-like. Maybe I'm sort of exaggerating too much of what it can do in the future. I don't know, but at least in my head, I think we should be able to at least make things better than what it is right now.
Okay, thanks, Aniket, for the remarks. Angel.
Oh yeah, I completely agree that having a bit of this affect will make the virtual characters much more engaging, and you could also imagine designing toys too. I guess they have these stuffed animals or whatever that talk to you, but they also are kind of stiff. So they could have more emotional gestures. That would be kind of fun for kids. And I do think there's a lot of value in education in these virtual environments. From a language point of view, you could even consider, teaching language, foreign language to students, and you can just visualize, these different concepts. A person being angry, or a person, some languages maybe they would use maybe the similar words, but some other language, or the same words to express two things, but some other languages would maybe have a fine distinction, and you can use that to illustrate the difference for either emotion or actions or spatial relations. Yeah.
Okay, thanks, Andrew, for the remarks. Thanks again for Aniket for the talk, and thanks Aniket and Andrew for this wonderful panel discussion. I think we touched a variety of topics, and I think it's very interesting. Okay, certainly this is a very exciting space. We are just getting started. There are many things to do in the future. Okay. All right. For the interest time, let's conclude this week's 3D GV seminar. Thanks everyone for the attention, and see you next week.
Yeah,
okay. Thanks, Angel. Okay. Okay. Bye.